Hi. What we are going to do in this presentation is learning how to set up linear programming model of different kinds so that you can see the number of fields that linear programming can help in business. But first we'll start with a short review on the problem that we had before, which was a prototype example on production control. And the problem was about the production of two products. One was called space rays and the other one zappers, where X1 and X2, the decision variables, represent the number of dozens of each product produced, X1 for space rays, X2 for zappers. This function is the profit function to be maximized. 8 and 5 are the profit per dozen of each product, and X1 and X2 are the number of dozens of each product produced. The constraints in the problem were of the resource type, the first two. So you have a resource of plastic and a resource of production time limited. This one to 1,000 pounds, this one to 2,400 minutes. And so the actual production plan cannot use more than what is available. 2 and 1 are the number of pounds needed in the production of pounds of plastic needed in the production of space rays, and 1 is the number of pounds needed in the production of zappers. 3 and 4 are the production time needed to produce a dozen of each product. So you see this is the total production time to not exceed 2,400 minutes. Two more constraints have to do with the structure of the solution. X1 and X2 combined cannot exceed 700, marketing requirement. And X1 cannot exceed X2 by more than 350, marketing requirement. This is the linear programming model. And we are going to skip a few of the steps we did last time and go to the procedure that solves the model and show where the optimal production plan resides. Okay. So, in order to find the optimal production plan, we have to limit ourselves to the feasible region. Feasible means that all the constraints are going to be satisfied by a production plan in this portion of the plane. Outside, it's infeasible because constraints will be violated. To find the optimal production plan means to find the plan that maximizes the profit. So therefore, we are looking at the profit function. The profit function is 8x1 plus 5x2. And we start with, say, a profit equal to 2,000. And then we draw a straight line that describes this profit. If there is a room for improvement, this profit is not the maximum. Improvement occurs when the profit increases. And so the line moves up. You see 3,500. Of course, you are going to continue until you maximize the profit. And therefore, the optimal production plan is in this place here, in which you produce 320 dozens space rays and 360 dozens of zappers for a profit of 43.60. One interesting observation here is where the optimal solution was found. So the optimal solution was found in what is called an extreme point. Extreme point is a point that is sticking out from the feasible region. There are several extreme points here. 1, 2, 3, 4, and 5. Feasible regions are built on straight lines that connect extreme points. But maybe this is an accident, and well, the fact is it is not. Here is another objective function, not the one that we had, and it's to be maximized. And when it is maximized, it stops at an extreme point, okay? And here is a third function to be maximized, and it will stop at an extreme point. So if there is an optimal solution to a linear programming problem, there is an optimal extreme point. I'm mentioning to you because I want you to know at the back of your mind that the program that we are going to use pretty soon, today, in a few minutes, that solves a problem with any number of variables is looking for extreme points. It is not looking for solutions that are interior point that will never be optimal. So it ignores most of the possible solutions and only limit itself to extreme points. So this was the main observation I want you to know from this graphical approach. And I think it's time now to move on to start setting up problems of different kinds of linear programming. Okay, so I'll stop the reshare and go to another file. It's another PowerPoint though, and it will show a few problems taken from your textbook. This set of problems is nice because each one represents a different area in business. And for each one, there may be an intervention of linear programming to improve the decision process. So the first observation, the first model is from marketing. In marketing, we are interested in many times advertisement campaigns that cost money, and it may be very expensive, by the way. If they are repetitive campaigns, then it becomes expensive. So you want to have a good use of the money. So this is one simple, very small example, again, with only two variables, but you can imagine that these problems can expand and becomes very large. And in this example, you have a restaurant. This is problem 2 in the book. There is a restaurant who wants to come up with an advertisement campaign and use local newspaper and radio ads. They dedicate $1,000 as budget for the campaign and set some conditions on how to spend the money. At least 25% of the budget will be used by each medium. You cannot therefore use only one single medium, only newspaper or only radio. Both needs to be used. Second is the amount that is allocated to newspaper ads must be at least twice the amount allocated to radio for their own reasons, which we are not going into at this point. We just want to express this as a linear relationship. Now, there is a concept called exposure created by the marketing department or maybe some consultant that expresses the efficiency of spending $1 on an ad. And it's different between the radio ads and the newspaper ads. It's an index between 0 and 100. The larger the number, the more the efficiency. Exposure, sometimes it's just the head count, how many people are exposed. And sometimes it has to do with purchasing power. But we are looking at it as a coefficient that goes into our modeling. So $1 invested in a newspaper ad will contribute 50 exposure units, whereas in newspaper, and 80 in radio ads. So the linear programming that we are trying to come up with should maximize this total exposure. If you put $1 in newspaper and $1 in radio ads, you'll get a total of 130 exposure unit. $2 in newspaper and $1 in radio ad will give you 100 exposure unit on newspaper, 80 of radio, for a total of 180 exposure units. So we want to find a plan that will use the money such that the exposure units are maximized. Well, you start your linear programming as we did in the first problem with decision variables. The manager needs to decide how much money to allocate to each one of these ads. Do not confuse this decision with the achievement that the manager wants to achieve. What he wants to achieve is to maximize the exposure. The question is how, and the how is answered by the decision variables. In each problem, you have to decide first, what do you need to decide here? So now we can build the exposure function. It's 50 times newspaper dollars plus 80 times radio dollars. Notice that we defined our variable as newspaper dollars as the amount of money used to advertise in newspaper and similarly in radio. So if 50 is the exposure contribution of $1 in newspaper, if you multiply it by the amount of money you put there, you get the total contribution of newspaper to the exposure. Now come the constraints. Notice that we have a budget, and the budget is used to advertise. So the expenditure on newspapers plus radio should be equal to 1,000. Then come the constraint on the 25% of the budget in each one of them. So the money in newspapers has to be at least 250. It's the 25% of 1,000. And the radio has to be at least 250. It's greater than or equal to. So to spend exactly $250 on newspaper is feasible, but also to spend 300 is feasible. To spend only 200 is infeasible. Then comes the relationship between newspapers and radio expenditure. So the newspaper expenditure has to be twice as much as the radio, at least. So usually students ask me, why is it that you put 2 here if the newspaper has to be twice as large? That's because it's already twice as large. If you write newspaper expenditure here and radio here, this one is larger than this one by how much? Twice. So for them to be equal, you have to take the smaller one and multiply it by 2. But it's not that they have to be equal. The newspaper has to be greater than or equal because it says at least. So this explains this constraint. Then comes the non-negativity, and we are done with this marketing advertisement problem. Okay. Just for you to see, I drew here the graphical approach. Still possible because we have only 2 decision variables. So I'm not going to develop it. You can take a look later in details, but I'll tell you one thing. Here is the budget constraint. And this vertical here is the 250 on newspapers, and this horizontal here is the 250 on radio expenditure, and you have to be above this one and to the right of this one because it's greater than or equal to 50. And what's interesting in this problem, oh yeah, you have another constraint here, that is the relationship. You can check to see that it's correct. But what's interesting is this constraint here. It does not say less than or equal to 1,000, it says equal to. So you must stay on this line to have a feasible solution. So therefore, this portion here that meets all the constraint on the budget constraint is the feasible region. But this region is reduced to a single line. So having said that, here is the optimal solution, you see? And that's the optimal campaign. But I don't want to deal with a graphical approach. I want to go first to a second problem, then move right away to the Excel formulation. The second problem is finance. It's from finance and it's about building a portfolio. As you see, it's problem number 4 from the text. A bank has some new funds available and he wants to invest them, and he is giving loans of 3 types. So it's home loans and personal loans and auto loans. Each one has its own rate of return. Okay. In portfolio building, normally and very naturally, we try to maximize the overall return, annual return, let's say. But some investments are more risky, some are less risky. So, and the return is not equal among all of them. So you give instructions to the finance manager telling him, this is how you can play with the money. At least 40% of the funds must be allocated to home loans. Home loans is the least profitable. So the danger is that you will just neglect it and go with the other. No, at least 40% of the funds must be in home loan. Usually if the return is lower, the risk is also lower. Personal loans cannot exceed 60% of the automobile loans. Okay, this is less profitable than this one. So the tendency is just to move with all your funds to the personal loans, but to maybe maintain some diversification. What happens, you say not more than 60% of the automobile loan will be in personal loans. Okay. Incidentally, such problems not necessarily always try to maximize the return. It also can be minimize the total risk. You have to build a risk function, try to minimize it, and it will be a function of how much money you put in each loan. Of course, then the best solution will be do not loan any money, because then the risk that you have of the portfolio is 0. No, you put in a return on the, as a constraint on the program, say your portfolio cannot have a return, annual return lower than a certain level. Now minimize the risk. This is another version of the same problem that I'm hoping we'll have time to deal with next week. But here we are trying to maximize the total return. So we turn to linear programming. We define our decision variables as home loans, the amount allocated to home loans, personal loans, auto loans. That's the amounts. The objective function, take a look, 7% rate of return times the amount invested there, plus 12%, plus 9%, multiplied by the amounts. The total is the total return, annual return to be maximized. Okay, so this is the objective function. Now come the constraints on the problem. Just ignore what's at the bottom here. I'm going to go to this in a few minutes. The newspaper plus the radio dollars. I think, what did I do here? Ah, I know what I did. Okay. Just a moment. I'm missing here a slide that will show the constraints of this problem. And yeah, just a moment. Here, that's one. The home loans plus the personal loans plus the auto loans has to be $1 million. $1 million is the budget. Home loans has to be at least $400,000. That's the 40% coming from here. And notice what happens here. The personal loans have to be less than or equal to the 60% of the auto loans. There is a slight difference between the way the last constraint is written compared to the first two, because in the first two, we have a constant, a value, a number written on the right-hand side, whereas here you have a variable written. The first two are called standard form constraints. This is non-standard. And in your textbook, I noticed that almost in every problem, there is a non-standard constraint needed. And for you guys, it will not make any difference. Solver, the program will solve it with no difficulties. The only thing you have to pay attention how you write the constraint when it comes to the spreadsheet. That's all. So I'll go over this with you. Okay. So now come the non-negativity, and the next will be the spreadsheet. So I'll have to go from here on. We are moving to Excel in order to formulate the problem. Let me just see where I'm standing here. Okay. Because yeah, okay. So we are going to go in order to Excel in a minute. I have to do some preparation for us, and this is back at the advertisement problem. Okay, this is the model that we just finished 2 minutes ago to set up for as a linear programming that solves the problem of a maximum exposure. I want to rewrite it in what you see at the bottom here, in what you see here in the bottom, because this will lead to how you set it up in Excel. The constraint here is newspaper plus radio equals to 1,000. There is no coefficient written here in front of newspaper and in front of radio, and I need a coefficient for Excel. I write 1 times newspaper and 1 plus radio. This way I don't change the value. And this is equal to 1,000. This is just a helper for you to know how to enter then the constraints in Solver, in Excel. Look at the second constraint. I have a newspaper greater than 250. So 1 times newspaper, because there is nothing in front of newspaper. But there is no radio, so I write 0 times radio. All the variables should appear in all the constraints with their own coefficients. So radio has a coefficient of 0, greater than 250. The next constraint has 0 of newspapers and 1 times radio. Oh, sorry. Okay. And then the last constraint, pay attention, 1 times newspaper, 0 times radio, no radio there. Greater than or equal to, and then you have to write 2 times the radio dollars. This will make a difference because when we go to Excel, you'll see why. Okay. So, and this is the next problem. I'm going to stop here. I'm going to go to Excel and come back to this later. Okay. Now, the Excel is here, and I'll share it with you. And we are on problem number 2. Actually, this is the problem taken from the book. I just cut and paste it for your convenience, if you want to read it later. And here is the model on the advertisement. This is it. You've seen it. This is the intermediate model with the changing of coefficient. It's changing, so to speak. We just added zeros whenever we didn't have a variable. And now I'm going to use this in order to enter the data into a spreadsheet format. Here at the top, name the variables. The variables name, so I'll call it, say, NP for newspaper dollars. The next variable will be radio, so it's R dollars. These are the two names of the variables in question. So these are the names. Here we have the variable values. Variable values. This is where you will find your optimal solution. This is where Excel is going to place the optimal values of your campaign. So all the variable values appear in these cells. I'm going to use them in the model. You don't put anything here. A solver will put values here. Next is the objective function, which is exposure. So I'll try to maximize exposure. You enter the coefficients, 50 and 80 here. You leave this one empty for now. We are going to fill it in with the total exposure, which will be here. Then come the constraints. The first constraint is the budget. Call it budget. Budget is equal to 1,000. Now notice the names that I'm giving here are my names. I enter them because it helps in identifying the details of the output. Very important when you have a larger problem and you might have 12 constraints. You want them named so that you know what is the result for each constraint. You want all the variables named so that you know which variable is what. And this is just a good practice. But it's just a name that you decide to give so it's easier for you to identify. Now, what do I enter here? The coefficients of the left-hand side being 1 and 1. You see here, 1 and 1. So I put here 1 and 1. Then leave this column Z, just leave it blank, don't touch it. And here, write the sign. The sign is equal to, and it's 1,000 on the right-hand side. The signs that you are going to write here are for your own good. This is a reminder for you because you will have to enter those signs in Excel in Solver later. The second constraint is the newspaper needs to be more than $250. So you can call it, say, newspaper dollars has to be greater than or equal to 250. You see, it's just a name. And so what do you enter here? The left-hand side, 1 and 0. Take a look at the constraint. You have 1 and 0. And now this one is greater than or equal to 250. Next constraint will be radio dollars is greater than or equal to to 50. Fine. So you have 0, 1, greater than or equal to 50. And finally, the last constraint on the relationship between newspaper expenditure and radio expenditure. So let's call it, say, newspaper versus radio. Okay, so let's see. I'm looking here down and I see 1 and 0, 1 and 0. Then I see greater than or equal to. And now you have to be careful here because you have a non-standard constraint. So you have to write that it's greater than or equal to then 2 times the value of the radio dollars. It's a function, so you write equal to 2 times, and now you have to multiply it by where the value of the radio expenditure is, which is here, Y2. And how do you know? You are going to tell solver that Y2 and X2 are the values of the two variables. So I'm using this cell. This is the linear programming model for this problem. Now, in order for solver to work, you have to do something that solver requires. Solver requires that all the functions that you are going to use are placed each one in a different cell, because solver can only work on cells. It cannot work on functions. For example, you cannot take the function profit, exposure and type it into solver. You will see when we go to solver where you cannot, solver does not understand it. Solver can only have a cell that contains the function. And because the exposure needs to be calculated here in the model, because solver needs to calculate and know the value of this exposure between different extreme points, remember? Solver focus on extreme points. For each extreme point that it's visiting, it has to calculate the profit and then decide which one is the best. So we have to provide it to solver. I write here a function called exposure. What is it? It's x3 times x2 y, because this is the exposure index per dollar invested in newspaper times how many units are invested, how many dollars are invested in newspapers, plus 80 times y2. This gives you the total exposure. It's 0 only because we didn't put any value here yet. Okay. Now, I'm not interested in the function so much as in the value so much as in the functions, because I want you to compare two such functions. And here I'm going to write down, so I'll move this one. And here I'm going to write the budget used, not the budget available. The budget used is what belongs to the left-hand side. So it's going to be x4 times the same x2 from before, plus y4 times y2 from before. Now you see the similarity between the two functions? x2 appears in both, y2 appears in both, because in both cases, it depends on how much money you put in each medium. In fact, every one of those constraints will multiply x2 and y2 correspondingly. So the only thing that is different between the first function and the second function are the coefficients. And the difference between the second and the third are the two coefficients. 1, 1 becomes 1, 0. So we want to write a function in which if you drag it down and copy and paste it row by row, we'll keep x2 and y2 unchanged. The only thing changing will be the coefficients. There is such a function that people are using in linear programming, and I'll delete the functions that I just wrote for you here and enter this function that I would like to work with. It's called sum product. What it does, it takes two rows of numbers or two columns, doesn't matter, same size. Take the first pair, multiply, second pair, multiply, third pair, multiply, and then take those products and add them. So that's why it's called sum product. But this is exactly what the exposure is all about. Take the first pair, 50 times what's in x2, take the second, 80 what in y2, find the result and add them. This gives the exposure. So here's how you enter the data that some product knows how to work. You highlight the first vector, I call it. You have only 2 variables, you enter 2 cells. If you have 7 variables, then you highlight all the 7. Now you press F4 right away. This enter x2 and y2 under this $sign, and if you drag, they will not change, which is exactly what I want. And then you enter the second array, 50 and 80. Okay, so now if you click outside, you get the sum product. It's 0 because I have no value here. If I had values, for example, let's say I have a campaign that is using $400 for radio and $600 for newspapers, okay? Then I get an exposure of 6,200,000 because 50 times 600 plus 80 times 400 is 62,000, okay? Now, I can apply this function as is by dragging it down to all the constraints because I'm going to do the same that I did to the exposure function. Example, you see this one? If, when I click here, the highlights are the first 2 rows, then when I click on 1,000, it will be the first one and the third one. Because I put $sign here, it will not move. Okay, and this one will be the first one and the fourth one. So that's what sum product does. And now you are ready to go to solver. Let me copy it back to where it belongs. Okay, and I can go now to solver. But you have to finish this before you go to solver. Remember, this one is, it's the objective value. This, all those are the left-hand side values of the constraints. Okay, solver. Solver will open. I hope you know that solver is an add-on that you activate exactly as you activated your data analysis in 361A. You go to, okay. So you go to file and you go to options, and there where you find all what you need. So you have add-ins here. And if you click on add-ins, you have 2 lists of add-ins here and here. If you did not activate solver yet, then it belongs in this list here. You highlight it, solver, and you click go. It will make it move to the list above. And then a little window, we have to check and okay it, and then it will stay here. Now it's activated. Once activated and you want to use it, you click on data. You go to data and then you find solver. Click on solver and you have it ready for you. It's waiting that you enter information. What do you do now? First, the objective function. Remember where it is. You know, many times I color this cell with some background color, yellow, red, or something that remind me that it's here. So you enter Z3 and make sure that it's a maximization of Z3, not minimization. If it's a minimization problem, you'll have to click there. This. Now you click on the changing variable cells, and here you enter the values, the cells where the variable value is supposed to be. We use those two, 1 and 2. This is the variable values. We are almost done. Now you have to enter the constraints. Okay, constraint number 1. It's waiting for you to enter the left-hand side, which is the sum product of constraint number 1. So here you enter the amount of budget you are using in your campaign. The constraint calls for equality, so you change it to equal to. The default will be less than or equal to. And then it's waiting for you to enter the right-hand side. So you enter the what is available. Go to the next constraint. What do you have here? You have sum product. This tells you how much money you put in newspaper, because you see you have 1 here and 0 here. So sum product, what does it give you? 1 times 600 plus 0 times 400. So it's 600. It's exactly the newspaper. This has to be more than 250. So you enter this. You enter this sum product. You change this one to greater than or equal to, and you click on 250. I want you to know that solver will accept a value. You can type the number 250 the same way you could type the number 1000 here. It takes a constant in a cell. It also takes a formula that was entered in solver in Excel into solver. You can enter this also, like I did here. But I am choosing just to enter this one to keep it consistent. So I enter the cell. And I'm adding another one here. And the left-hand side, again, is greater than or equal to the right-hand side. Again, a cell. Finally, we have the left-hand side is greater than or equal to, and here you have a cell. The cell contains a formula. 2 times y2 is written inside here. It became 800 after the 400 was thrown into this cell. So you click on this cell now. You cannot type 800. This will be wrong because it's only 800 once the 400 is here, and this has to be more than twice. It is more than the twice. 600 has to be more than twice that 800 is, and it's not true. So this solution is infeasible, you see. I just gave you an example of hypothetical solution, that's all. And we are done. We entered the model. You see the 4 constraints, you see the variables, you see objective function. All what you need is to make sure this is checked. It will be unchecked if it's the first time you solve a problem today. If you check it and you solve second time a problem and you didn't close Excel, then it will remain what you had last time. But it has to be checked because it has to do with the non-negativity. And it tells solver that you are using non-negative variables. Then comes an important selection, and it's here. The default, usually it's GRG nonlinear. It's a name of an algorithm. It's not the one you are using. You are using an algorithm that does linear programming, and it's called simplex. So you will always select simplex LP. LP is linear programming. And this is it, you're done. And you got the solution. This campaign will maximize exposure at a level of 60,000 units if you put $667 in newspaper, $333 in radio ads. All the constraints are met now, all the constraints. This one is 1,000 if you add them. And this one is more than 250, as you know. This one is more than 250, as you know. And this one is exactly twice 333. So the two constraints now, the two sides of the constraint are now equal to one another. This is what it's called to solve a linear programming problem. Okay? The loan problem. That's the home loan and personal loans and the auto loans. I have a solution for you here already, but I'm going to delete it because I want you to see how to enter the data. And since we just finished that problem, I'll take a shortcut here. Incidentally, what's underneath here is something we will use later. It's about sensitivity analysis, a big topic in linear programming that I'm dedicating a different meeting for that. So the model was, here is the 7% rate of return, 12 and 9% for each loan. These are the coefficients. So here's the budget. It's home loan plus personal loan plus auto loan dollar values, when you combined, should be equal to 1 million. So therefore you have 1 and 1 and 1. Then it says that home loans should be at least 40% of the budget. Therefore you have 1 and then 0, 0. Has to be at least 400,000. And here it says that personal loan should not be more than 60% of the auto loans. So the 1 is here, 0 and 0 are here, and it's less than, now let's see what, 0.6 times 0.2. Sorry. So it's 0.6 times 0.2, it's because it's 60% of the value of auto loans. So therefore I multiply 0.6 by auto loan value. It's very similar to the model, similar constraint in the previous problem. So now comes the sum product. Take a look. See? Here I highlighted the 3 variables from M2 to O2. From M2 to O2, and pressed F4 to get the $ on them. And then came the coefficient for the return. So it's M3 to O3, close parentheses. Okay. Then I copied them all the way down, and I found the left-hand side of the constraints. That's for solver. In solver, we did what we did before. We entered, here's solver. So when you save a problem, if you have a solver model and you solved it, and now you save the file, and tomorrow you open it, it will open it when the solver model will remain. So P3 is here. P3 is the objective value representing the annual return, dollar value of the return. It's a maximization. The variables are M2 to O2, so it's here. And the constraints have been entered as we did before. When solved, you got the optimal portfolio that tells you to loan $1,000 under home loans, $225,000 personal, $375 auto loans. If you do that, your rate of return per year is maximized at $88,750. So what I need you to do, guys, is to practice such problems. I'll send you an email tonight with suggested problems. Try to do it before Thursday. Like 3-4 problems, all similar in all of them, even if asking you to do the graphical, do not do the graphical. Just do Excel, because I want you to get ready for larger problems, maybe next week with more variables. And certainly I have in mind one such problem in logistics that are the number of variables and constraints in logistical problems, humongous. We will not have this large scale problem, but you will see how fast the number of variables is growing. So I want you to have the feeling of this solver software, and I would like to solve. I want you to know that you have a short tutorial for using solver in the book in chapter 12. If you read the first few pages, I'll give you the reading when you'll get the email, and also the problems that I think you should do. Solutions to the problem appear on the website. I put the solutions to all the chapter, and that's it. Now, to remind you, there are office hours that I scheduled. They are aside from our regular website Zoom meetings. They just come to replace the office hour that we had before. That is, if you need them. And if you do, I'm hoping that you will send to me your questions beforehand. This way we can use our time better, because then I can do preparation if I need to. And so this is it for today. I hope you take a look, and I hope you do what you are supposed to do, and we'll be fine. Okay, bye-bye.